Okay, let's finally talk about the discrete Fourier transform full on. So I'm going to talk about something called the real value discrete Fourier transform. And I'm going to define this maybe in a slightly different way that you would see other places, just so that it matches with the observations we've made so far. And then later we'll talk about something called the complex valued discrete Fourier transform, and we'll use complex numbers. But for now, will the real DFT please stand up? Okay, so we're doing the real DFT. Now, so the idea is we just saw that you could shake out different sines and cosines by using a probe frequency that was a pure sine or a pure cosine that went through an integer number of periods. And if you did the dot product of that probe with your signal, then the dot product would be 0 if the probe was not at all in the signal, or it would be non-zero if the probe was in the signal. So what we're going to do is try a whole bunch of different probes and record the dot products of each probe. And so what we need actually is, so let's say that I had a signal that was 40 samples. Well, I'm going to need, turns out, 20 cosines and 20 sines as probes to uniquely represent this signal. If I go beyond this amount, what you'll see, let me show you real quick if I go beyond 20. So it's really the ceiling of the number of samples over 2. If I go beyond that, what you'll start to see is the frequencies will start to come back the other way. So I start off low frequency. In fact, I start off 0 frequency, where it's a cosine of 0, which is 1 the whole way, and sine of 0 is 0 the whole way. I go up, and then once I get halfway through, I start to come back the other way and slow down again. For the sines, you do that, but you have a phase change. So we'll talk more about that later, but for now, let's just stick to using the half of the ones that aren't redundant. So I'm just going to use, okay. So 20 sines, 20 cosines, 20 sines, that makes a total of 40. So I'm going to have 40 new numbers. Each number is going to be a dot product of my signal with one of these sines or cosines. So I started with 40 numbers. Now I'm going to shift to a new set of 40 numbers. It's like putting on a different pair of glasses. I'm going to look at it and say, okay, which one of these cosines and which one of these sines showed up? So let's define it here. So there's 2 parts to it. So we're saying given a signal a signal x with n samples, we're going to define the cosine parts. And this will be the dot product of x with different cosines. In particular, if I write it out mathematically, it will be the sum from, we'll say I equals 0. So let me say it this way. C at index k, so the kth cosine, will be the sum from I equals 0 to n minus 1 of, so we're just going to do the dot product. So we're going to say x at index I times our cosine at index I. Well, our cosine at index I is going to be 2 pi. Actually, sorry, let me say, instead of I, let me use conventions that you see more commonly. Little n is what I'll use. Okay, so sum from little n, that's going to be our index. Little n equals 0 to n minus 1. X at index n times cosine of 2 pi little n over n. And then we also need to multiply by the frequency that we have here. So the frequency that we have is k. Okay. And so we do this from k equals 0 up to n minus 1. No, sorry, the ceiling of n over 2 here. Okay. So let's look at this. So here's our formula. Whoops. Need my equal sign there. So this is just a dot product. So I have my array, x, and then I make another array, which is the samples of my cosine. I take n such samples. If my frequency is k, this will go through k cycles over an interval from n equals 0 to n minus 1. And at every sample, I take the multiple, I multiply it by the corresponding sample in x, and I sum them all up together. So this gives me my cosine component. So there are n over 2 of them. So for every k, for every index here, I get a different cosine. I also have the same exact thing that I'm going to do for sines. So there's my cosine part. Here is my sine part. So I'll just call it S of k. So, and whoops, I already, I want to start over there. I'm about to do this in code, but let's just write it mathematically first again. Just the cosine changed to a sine. Everything else is exactly the same. Okay, so let's just translate this into code real quick. So I'm going to return two arrays. Each one has about n over 2 samples in it. So the number of frequencies that I'm going to consider is the ceiling of n over 2. Let me make my samples of the cosine. So I'll say n is equal to np.arange, and I also have to say n is the length of x. So n is equal to np.arange n over n. So that's going to make all my n's that I'm going to use to sample my cosine. And now what I can do is loop through, and for each frequency apply this formula. So I'll say, okay, I need to allocate space for my cosines and my sines. And in these arrays, I'm going to hold the dot products. Okay, so let's do the cosine first. I'll say, and let me be completely consistent with my notation. Okay, so C at index k is equal to the sum of this dot product. So that would be x times, and then we've got a cosine of 2 pi k n. Let me be fully consistent here. Okay, so n ranges from 0 to n minus 1. That's what a range does. And I'll divide that by n. Okay, the sine should be the same thing, just a sine instead of a cosine. And now let's go ahead and return this. Okay, so I return my cosine part and my sine part. Cool. So let's see if this works. So down here, I'm just going to make a signal which goes through 2 cycles over this interval. And let's plot this. So I'm going to call my DFT, and I'm going to plot the result. Okay, so what we see is, all right, so this is should be 2 hertz. We see a peak in the bin and the cosines at index 2. The sines are pretty insignificant. Okay, so this makes sense so far. Let me increase the frequency to 4 hertz. And now what we see is, okay, this shifted over to bin at index 4. And the sines are still insignificant. If I add a phase to this, remember what should happen? So let me add a pi over 4 phase, which will split it evenly between sine and cosine. Now I see I have, this much in cosine and this much in sine. Now I want to depart from canon a little bit. I want to slightly tweak my definition so I can interpret these values a little bit better. So one thing that we noticed when we did the integral last time is that if the probe frequency was there, we ended up getting, if we looked at an interval from 0 to 1, we ended up getting n, or sorry, 1/2. We ended up getting 1/2, right? So if I go back and I look at, I believe this was the notebook I was looking at. Yep. So remember when we integrated, we got a half if the frequency was there. Just the same way, if you integrate over, if you sum and do the dot product over an interval of n, you're going to get n over 2. So let me actually divide this by n over 2 so that it comes out to be truly the amplitude of the sine and cosine that we get. So I just want to normalize this. Okay, so I see in this case, turns out that the amplitude of my cosine should be root 2 over 2 actually, so slightly less than 1. And amplitude sine is negative root 2 over 2, so we see that. Okay, so that's interesting. Now I keep saying amplitude. Well, okay, let's look back at an equation for a sinusoid again. So, my sinusoid can be written as y then is equal to cosine 2 pi f times t, and then we'll say just plus phi, which can be written as, okay, and actually let me be even more general here. Let me consider an amplitude in front of this sinusoid. So it's not necessarily a unit sinusoid. It could be greater or less in amplitude. So here's the sinusoid, but we can rewrite this as, so I'm really going to use the same trick I used before, but this time I'm going to actually pull out the amplitude as well. So I can write that as a cosine of phi, cosine of 2 pi ft, and then plus a sine of phi. Remember, actually it's a minus here, minus a sine of phi, sine of 2 pi ft. Okay, so if I tweak my definition here a little bit, and I actually scale my thing down, I mean, these are all different things that you think about. There are various reasons for doing this and for not doing this. So I don't want to talk about them right now, but I'll just mention for people who've seen more math that you actually might want these to be unit vectors. These cosines and sines. In that case, you would actually divide by 1 over square root of n. But here, I want to know, well, what are the amplitudes of my sines and cosines? So what I'll see is if this is the sinusoid that I give, and I probe it with a pure cosine, under the definition I just made, I should get a times cosine of phi. If I probe it with the sine, I should get negative a times sine of phi. Well, let's just look real quick. You know, I gave pi over 4, right? And my amplitude was 1. Well, so what's the cosine of pi over 4? So let's just print it out, and let's print out the sine of pi over 4. Okay, so and actually negative of that, right? Okay, so my amplitude was 1. And so that's what I got. And you can see that that matches down here. So there we go, 0.707, negative 0.707. Let's just look at another example. So what if I did plus pi over 3 instead? So I would predict that the amplitude in front of my cosine term should be a half. The amplitude in front of my sine term should be negative 0.86. Let's see if that's true. Sure looks like it, right? So what we see is this is looking almost like a negative sign. A negative sign would start at 0 and go down right away. This starts at 0.5 and goes down a little bit. Just to point out, actually, you can turn, if you use a phase of, so if we subtract pi over 2 here, so the cosine is an even function, turns out, so actually the negative doesn't matter. But here, this would then turn this into a positive pi over 2. So if your phase is negative pi over 2, that actually turns this into a sine. This is a trig identity. So just to check. Okay, so we see we get basically nothing, a really tiny number for cosine, and then 1 for sine. So if I make this phi, if I say minus pi over 2, I end up turning the sinusoid into a pure sine wave. Starts at 0, goes up, and goes down. And now the cosines are insignificant. So that's something that's helpful to remember, is actually, so the trig identity is that cosine of, you can say that sine of x is equal to cosine of x minus pi over 2. So that's the identity. Okay, so I just wanted to point that out. But the other reason I made such a big deal about the amplitude here is because there's yet another trig identity I can use, which is even if I don't know what the phase is, I can figure out what the amplitude is. And even if I don't know what the amplitude is, I can figure out what the phase is. So let's see how we can do that. So notice so I know that, okay, so let me come up with a name. So I'll say yn is equal to, I'll say a times cosine 2 pi ft plus b times sine of 2 pi ft. So I'm just introducing variables where a here is equal to big A times cosine of phi. So let me write that down too. So I'm just saying that a is equal to big A times cosine of phi and b is equal to big A times sine of phi. Okay, so I'm just defining a couple variables here. Well, here's an observation. So a squared plus b squared is equal to big A squared. Well, how could that be? Well, this is where we have to use the Pythagorean identity, because, okay, so a squared plus b squared. So this is another trig identity, which you should have seen at some point. A squared plus b squared, well, that's the quantity a cosine of phi squared, which would be a squared cosine squared phi, plus a squared sine squared phi, which, okay, we can factor out the common term of a squared here, and then we get cosine squared phi plus sine squared phi. But actually, cosine squared of some angle plus sine squared of that same angle, that's always going to be 1. That's the Pythagorean identity. That's the fact that cosine and sine come from the unit circle. The unit circle's equation, so the cosine of the unit circle gives the x component, the sine gives the y component. The equation for the unit circle is x squared plus y squared is 1. Therefore, cosine squared plus sine squared is 1. Cool. So actually what we can say is that if you do the probe with a cosine and you do the probe with a sine, you get these numbers a and b. You can actually determine the amplitude by saying a is equal to the square root of a squared plus b squared. Okay, so that's how you get the amplitude. You probe it with the cosine, you get this number a. You probe it with the pure sine, you get this number b. The amplitude is the square root of the sum of the two squared. Okay. So that's cool. And also this matches, I mean, it's really a lot of Pythagorean stuff going on here. If you think of this cosine and this sine, these samples as a vector, you're really projecting it down to 2 dimensions in a high dimensional space. And this is the length along those 2 dimensions together. Okay. You can also determine the phase. So this is kind of cool. So if I say, I'm just going to write the formula, and I think you'll see, we can look and see it's true. So so the phase can be written as the inverse tangent of b over a. So you remember that the tangent. Okay, so yeah, let me just verify this. So this is you know, if I check this, let me plug in b and a. So b is a times sine of phi. A is a times cosine of phi. Okay, so what we remember is that the tangent is its opposite over adjacent, which also can be written as sine of phi over cosine of phi. So yeah, so I see the a cancels out here, so I can actually write this simply as the inverse tangent of sine of phi over cosine of phi. Well, if I'm given sine of phi over cosine of phi, I'm given the ratio, I need to go back to an angle, I just take the inverse tangent. So you can actually get both the amplitude and the phase with these equations. So amplitude is the square root of the cosine amplitude squared at that frequency plus the sine amplitude squared. The phase is the inverse tangent of b over a. Now we have to be a little careful with this. There's some ambiguity. If this could be a positive number if both b and a are positive, it could be a negative number if one of a or b is positive, so we're not sure. So in practice, what we do is we say the phase is equal to numpy dot arctan2, and then we give it the y first. So the y is the sine component, so the x is the cosine component. And this actually resolves the ambiguity. So there's a special function in Python to do this. So this is extracting the phase. The amplitude is even simpler. Let's see, what did I call it down here? I called it amps. Okay, amps is equal to the square root of the sum of the cosine component squared plus the sine component squared. So this is, I'm doing element-wise numpy operations here, so this is going to do it for every pair of cosine and sine. So let's now have a look at this. It's not plotting the phase because I need to comment this. Okay, here we go. All right, so I just showed you that I gave this a phase of pi over 2, right? So that's neat. Let me go back and give a phase of pi over 3. Okay, and actually, hang on, we're getting some weird stuff going on with this sign here. So this actually says negative pi over 3. Yeah, this gets a little weird with the signs here. Let me be very careful. Yes, I forgot to factor the negative sign through when I was doing these things before. So I should have been a little more careful. It doesn't affect the amplitude, but I should have said that the phase was actually this is actually should be negative b over a. Okay, I'm kind of breaking some conventions because I'm trying to not use complex numbers right now, and it kind of threw a wrench in the works here. But it's not a huge deal. It's just yeah. So this would be negative a sine phi. So this would turn out to be negative. Okay, so I just needed a negative sign there. See, even if you have math bugs, it's just a math bug. That's all it is. You can work it out. So let me go to my tangent. I need to throw a negative sign in here. Okay, that fixed it. All right, so now I see my phase is pi over 3. Let's just check it and see if we get some other examples here. Let me actually make the amplitude larger. So let me make the amplitude or smaller, let's say. So let me make this maybe 0.5 times cosine of 2 pi ft times, or I'll say let me add a phase of 2 pi over 3. Okay, let's see what this looks like. Okay, so I see the amplitude went down to 0.5. Cool, so when I took this, I have the same frequency index. I'm at frequency index 4, right? That was the one I used. Yep, okay. So I can see that's the only one that actually has a non-zero amplitude. I can see it has a little more sine than cosine, but they're negative, and the phase is 3 pi over 2. Or 2 pi over 3. Okay, which is less than pi over 2. There we go. So I just want to show you one last thing with the phase. You get these neat patterns when you time shift a cosine or a sinusoid. So right now I can see, okay, let's wait until, okay, so now it's fully a cosine, but it's shifting over, it becomes more of a sine. Now it becomes a negative cosine, now it becomes a negative sine, and now it goes back to being a cosine. So you can kind of track these phase changes as you go. And actually you can watch the phase here. So it starts off 0, so it's pure cosine. Now it's pi over 2, now it's pure sine. Now it goes beyond pi, it's a negative cosine. Now we're back to 0. Anyway, okay, so that's that. But the amplitude stays the same the whole time. So the square root of the sum of the squares of the cosine part and the sine part is 1 the whole way through in this example. I could do the same thing on a higher frequency cosine. So here I see that this actually index 5. That's going to peak, and actually the phase changes faster here. Because if we go back and look at our equation for shifting over time, it's actually, f of t is equal to cosine of 2 pi f t minus my shift, right? But actually, to get a phase out of that, remember I expand this, and I say, well, that's actually 2 pi ft, and then the phase is actually minus 2 pi fs. So if f is larger, the phase is going to change more quickly for the same shift. So if I compare this plot up here, where it's only 2 hertz, to this plot down here, I can see that for the same shift amount, the phase changes more dramatically. So in a moment, I'm going to show you some really cool patterns that come out of this with more complicated waves. But that is the basic idea of the discrete Fourier transform and its phase and amplitude. Okay, so just a quick exercise on that.